the high power laser systems. So thank you very much for our members for that. And remember, we are here in San Jose because today, tomorrow, and the day after, we have our co-package and pluggable optics event. And all of you who are interested in quantum technologies, on the 8th and 9th of November, our Quantum Industry Summit with an executive agenda of CEOs. And we just heard that the Nobel Prize winner in 2022 for physics, Alain Aspect, is going to be with us, giving one of the first presentations as a laureate. This is big news for us. Thank you very much, Alain Aspect, for being with us and giving the presentation at our first Industry Summit of Optica in Europe. This is big news for us. But today is all about LiDAR. It's about LiDAR miniaturization. And as I said before, we have a great, spectacular agenda with Pioneer, John Deere, LiDAR Tech, or well-known consultant Sabir Ramvala, and then we have the US Army and Aurora. What we really want is to make sure that all these people get connected with a global industry network. And the most important part of the meeting is that if you want to get in touch with any of the participants, all of you are going to get the participant list. If you want to get in touch with any of the participants, all you have to do is send me an email, jpost@optica.org, and I will make sure I do the introduction. Please remember that this meeting is about cooperation. And also, this meeting is also live streaming YouTube. So we are live in YouTube as well. So allow me to say hello to the YouTubers. Hello, YouTubers of the world. If you have any question, please read it in the chat and we'll read it in the room. But remember, this meeting is going to be also available for offline view, later on view at your own time. So make sure that whenever you watch this meeting, if you can find an opportunity to collaborate with any of the participants, let us know and we'll make the introduction. And with this, I would like to kick off the meeting first by saying that we really have been overwhelmed by the interest of the industry from these meetings, but also by saying that our first speaker today is a person that means a lot to Optica and means a lot to me in particular. He's been engaged with us for many years, giving keynote presentations at many of our events, and today is our first speaker on our first online industry meeting on LiDAR. Thank you very much, Jan-Erik Karlheimer from Pioneer, to be our first speaker today. The floor and the attention of the Optica network is yours. Jan-Erik, you are muted. While he unmutes himself, let me remind everyone to connect your screen.
I'm a male. I have to do two things at the same time, and that's overextended. Let me see if I can.
If you go to slideshow mode, presentation mode, then we are in business.
Do you see my full screen? Or is it the thumbnails?
I think it's coming. While it comes, I would like to remind everyone to please keep your camera on at all times. This is a meeting. It is not a webinar. We need to make sure that you are there. As my friend Elise Fritzke says, if you go to a meeting, a live meeting, you don't expect to be hidden under the table when you are not talking, right? So this is the same. Please keep your camera on. I think we still have a problem with your screen. Jan-Erik Karlheimer, can you please click again? Do you have two screens in front of you?
Yes, I have two screens.
So I think you may be sharing the wrong screen with us. So if you don't mind, please stop sharing the screen, start sharing the screen again. And when you click share screen, select the window that you want to share with the universe.
Okay, let's try again.
I have a lot of friends in the room. I would like to say hello to Chris Maloney from VPI, Dario Locascio from Microline, Samuel Schwenger from Jabil, Yoshiaka-san from Sumitomo Electric. Great to have you here.
So do you see the right screen now?
Yes, now it's perfect. The floor and the attention of everyone goes to Pioneer.
Sorry about that. So first of all, for requirements, especially on automotive, I mean, it's the obvious ones: low cost, low weight, low power consumption, small package, recyclable, etc., and so forth. So they are, of course, the targets, but you also have to fulfill the functional targets. And for functional targets, I want to remind that range, there's a lot of talk about range and resolution, but range and resolutions are connected. So the range determines how fast you can drive in automated mode, and resolution determines how small objects that can be classified. So range without resolution is not enough. So minimum required resolution is determined at target range. Or if you don't have enough resolution, your effective range is what your resolution gives you. There is a pending new regulations. It was passed in the ECE, so probably will come to the US with FMVSS eventually and things like that. But will allow L3 automation up to 130 kilometers per hour, roughly 80 miles per hour for those in that units, and with a range of 160 meters, which comes from current automotive RFIs. And to see a target of height of 0.12 meters, like that's 5 inches at tenths of a mile. And that object can be typically a broken tire. That means your vertical minimum resolution is 3/4 of a milliradians, or 0.04 degrees, 400ths of a degree. And then you need some more points in order to classify it. And assuming 4 points here, that means that we are at 1/100th of a degree in vertical resolution. Just to compare it with what a lot of people are familiar with from the Google car in the early Velodyne, the point separation there is 0.9 meters. So you get at most 2 points vertical. So it just gives you some perspective that if you have to see something that is, it gets several points on something that is 12 centimeters tall. So, and this is the UN regulation. It was passed on the 22nd of June. So if you want to read up more, but it actually allows L3 up to 130 kilometers per hour. And I think that gives a lot of the requirements. The next point I want to say is that it also has to work in a lot of different weather conditions, unless we all move to Arizona or other places where they have very nice weather. And this is an example of what we can see. The left one is driving behind a car on wet road, and the other one is driving behind another car on snowy road. Rain is usually not the main problem. The problem is the wet road and somebody driving in front of you, but your system has to handle this as well. And with that, I close my talk.
Thank you very, very much, Jan-Erik, for being with us today. And thank you for this nice presentation. This meeting is all about cooperation. So we have a question that we ask our people, which is, what kind of challenges do you have? What kind of things you think the rest of the industry is today here with us can help you with?
Well, I think that for automotive, I mean, the first requirement is cost, and the second requirement is cost, and the third requirement is cost, but you always have to fulfill the specifications to solve the problem. And you have to be small, and you have to use little power, and it has to be possible to package and so forth. But unless you fulfill the requirements, the use case requirements, and this automated highway driving is actually a real application that's coming to cars in the near future. And that means that there will be lots of systems requiring these things on the road.
This meeting is to connect the end users with potential integrators, with potential technology providers. Jan-Erik, stay with me because I have some questions for you. But to make it more complete, I have another company who is addressing a different market, which is the space market. Optica corporate member Scanway is here with us. Mikolaj Čech, connecting from San Jose to Poland. It is great to have you. Could you tell us a bit what Scanway do and what is your interest in LiDAR?
Yes, of course. If it's possible, I will share the screen. I have one slide which should clearly say what we are doing and why the LiDAR is in our interest. So basically, as Jose introduced me, my name is Mikołaj. You can call me Nick in English. It might be easier for you because of the Polish names, which are quite complex to pronounce. We in Scanway, we are, let's say, leading entity in our part of the Europe, which develops optoelectronic systems for space. And therefore, we have lots of interest for LiDAR. Quite recently, you probably all hear about the number of satellites sent to space by Elon Musk and about the space degree. We are working right now with our partners to integrate cameras and potentially the LiDAR systems into one complex matrix of sensors, which could be used to operate the spacecrafts and satellites in orbit. So there is a huge market coming for these kind of systems. So we are open for any cooperation, for any R&D, not only in space, but also in different, let's say, maybe slightly weird areas of industry, like, for example, the wind turbine maintenance industry, where we have implemented LiDAR as a quality inspection system of wind turbine blades. So space is one thing, but there is room for LiDARs here in Poland and in Eastern Europe in general. So if you have any questions or things to potentially discuss, feel free to contact me here or through Jose. Thank you.
One thing that I would like to ask the two of you, of course, you come from very different market segment. On one hand, we have Pioneer who tell us that the biggest challenge is the cost. Mikolai, for you, is also the biggest challenge the cost, taking into account that you're going to higher and higher volume production because of the CubeSats?
Well, not necessarily the cost. I would say that the availability of the components right now is the bottleneck, as well as the unstable situation on the markets, which is connected to the geopolitical situation in Europe. It's kind of crazy right now. So both of these aspects will be the key drivers of the company's development in our sectors, I guess.
I want to connect these two companies with one other company that means a lot to me, a person that I have been in touch with many years. This person is from Jabil Optics, Simon Schwinger. Thank you very much, Simon, for being with us. Jabil Optics, I think all of you know Jabil, one of the largest companies in the optomechatronics manufacturing in the world. Simon, when it comes to LiDAR and hearing the specifications and need of a company in automotive and a company in space, what do you bring to the table?
Hi, Jose. Nice to meet you here. And you guys, can you hear me?
Loud and clear.
So I would have something I could share also one slide with you, if that's possible.
Yes, please. And while you share it, I would like to remind everyone to please keep your camera on. We really want to see everyone. Emil from Synopsys, great to have you here.
All right.
Jabil Optics, for those of you who don't know, is in Jena, the capital of optics in Europe. Last week I was in the capital of optics in the US, in Rochester.
Can you
Here,
can you
yes, now it's good.
All right. So just a few thoughts that we see on LiDAR, of course, and I think we share the view. It's a key technology for autonomous driving. It will be part of the sensor suite enabling this technology. However, what we also see is that the expertise and infrastructure to design a product, the LiDAR product, for mass production is underestimated. And why this is the case, I'm going to explain in a little more detail. What we also see is that there are a lot of startups involved in this technology, and some already start to fail, and I think there will be more coming, and it's not, to our perception, because of limited funding, even though the funding also is sometimes not very substantial. And most of the startups die because they are not capable of coming up with a product that is mass manufacturable and has the potential to scale fast. And I think that's also a key topic here. And why is that? We tend to say that there's many complex technology-specific challenges. First of all, it's in numerous parameters, and the colleague from Pioneer already highlighted some of the parameters, and there are many more, right? Also, we say a lot of key components that are still under development, like MEMS devices that are currently being developed, but at the same time being integrated into a LiDAR system. That adds complexity. Plus, during design engineering, you need to maintain a lot of flexibility to adjust to changes throughout the project. And this is very to the contrary of a very highly structured mass production environment. So this is really attention that is brought in and we experience on a daily basis. Plus the interfaces that already have been mentioned by the colleague from Poland. I hope I didn't recall your name, but markets, regulations, supply chain constraints, that adds to the complexity. And Jose, if you may allow, I think Jabil is in the position to answer these challenges So we have startup mentality. We are the second largest manufacturing provider, 260,000 people, 33 billion in revenue. We focus on design needs. There doesn't need to be an outlook on the mass production. We understand it might take a while, but we provide this access to engineering and also manufacturing experts. And we are happy to share and continue to share our thoughts in this call today and also afterwards.
Now that I had to see you engaged, now one of the key questions I want this meeting to try to answer, and I want to go to each of you, Karl-Heinz, Nikolai, and Simon, one after the other. What is the right wavelength that we should target for LiDAR in your particular application? Jan-Erik, Veoneer, what are the current issues with eye safety? What is the recommended wavelength for LiDAR?
Well, there are probably many different opinions about this thing, but I take the functional hat on here, and it has to be eye safe class 1, and it has to fulfill the specifications. If I can do that with call it the silicon wavelengths, it's probably cheaper than it's preferred, but it has to be eye safe and it has to fulfill the specs. And I outline what I now think is the most relevant dimensioning spec on highway automation. So you won't give me a number, but if you can solve it with a cheaper technology, that's preferred.
Nikolai, where do you stand with wavelength? You are talking about large range LiDAR here, so you don't have problem with eye safety, but you have problem with power.
Yes, exactly. So there should be a compromise between the power and the range, and basically the parameters of the quality parameters that we can get from the LiDAR. In space, as you mentioned, the eyes are not that problematic. We need to be able to to have the precise measurements up to hundreds of meters, and we not necessarily have to carry the nuclear power on our backpack. So that's very tricky, and that might be the biggest challenge actually to answer that question and to find different solutions, different ideas. For example, we can have different solution for small satellite, we can have different solution for bigger satellite because of the power. So that's at least for me right now, it's very, very hard to give you any number. It would be the matter of discussion and some kind of feasibility studies, that's for sure.
Thanks, Nikolai. And then the other one, then Simon, you're from Jabil, one of the largest camera manufacturers in the world. You've had both work on silicon photonics in the infrared, as well as one of the biggest customers of our VCSEL manufacturers in the 840 and 790 nanometer wavelengths. So what is, in your opinion, the most interesting wavelength for LiDAR? Where should we go in terms of wavelength?
I think you already got an idea from the previous two answers. There's no straight answer to that. There's always a discussion on trade-offs depending on the application. So the position we take here is really, we try to be technology independent. So we're looking into frequency FMCW LiDAR or solutions like that as well, where the components that go into there tend to be a little more expensive. And there are other applications where you can use more of the already available components. But there's no straight answer, and it really needs to be discussed in detail.
My friend Ralph Munster from Silk is here for talking about FMCW LiDAR. I'm going to ask him in a bit to talk to us about this. But before that, when I hear from Veoneer is low cost and high safety. When I hear from Scanway is high power. And when I hear for you is that is integratable, that is also cheap, and it is suitable to other technologies. When I think, when I put all this together, I think about VCSELs, and I think about VCSELs in the longer wavelength, in the infrared VCSELs. I have been discussing about this with my friend Christian Neumeyer, CEO of Vertilas. Christian, are you with us today? I would like to bring you now to the discussion because I know that you have a big achievement in terms of high power at 1.3 micrometers with VCSELs.
Yeah, that's right. Hi, welcome everybody. I can quickly show one or two slides maybe.
Yes, please.
Let me try and share my screen. Right. All right. You should be able to see my screen now.
Yes.
All right. I hope it's good enough. So
let's
yeah,
go
so
to a presentation mode, a slideshow mode, so you can see it bigger.
okay, cool.
Because this is a very important part of the meeting right now, making the first amendment. Yes.
Right. Okay. All right. So we have a long wavelength VCSEL technology. So it's based on indium phosphide. So I think the big or important part of it is that we can produce VCSELs from 1.27 micron all the way up to 2 microns. So we can do 1.3 micron VCSELs. We can do 1350 nanometer, 1380 nanometer. We can do 1490, 1550, any kind of wavelength. And we have started to produce now 2D VCSEL arrays for like 3D sensing and LiDAR applications. I want to show you some examples very quickly. Target applications, you know better than we do. But if you look at like the availability of prototypes or 2D array chips we have today are at 1.3 micron, starting from a few emitters all the way up to 800 emitters. And the 800 emitter device, let me just see, produces up to 8 watts in QCW mode. So, and if you pulse it, you get a multiple of optical power of it. Another example is like a 300 emitter array, which produces about 3 watts of optical power in QCW. And if you pulse it like with a 200 nanosecond pulse, you get almost 5 times as much. And of course, if you even reduce those pulses, then you get even more optical power out of it. And you know, as I said, we can do the 1.3 micron, like 1380 nanometer, which I think is probably the best to work with sunlight interference in the open space. But we can have any kind of wavelengths between 1.3 and 2 micron. And we can structure from a few milliwatts up to tens of watts of optical power, you know, integrated on one chip. And then you can, if you need even more power, you can integrate even more emitters on one chip, or you can integrate several VCSEL chips in one package.
You get 14 watts of power at 1.3 microns?
Yeah, and this is only a 300 emitter device. You know, the other one is an 800 emitter, which has about 8 or almost 10 watts peak power at QCW, and you get maybe probably like with a 200 nanosecond pulse, you get like 30 to 40 watts in that range. Yeah.
This has resonated with 2 people in the room. First, Sabir from Patience Consulting. Sabir, thank you very much for being with us today. What's on your mind?
Yeah, no, I think the question I had, I think this is great. I think Trump also released some information recently about indium phosphide, you know, long range VCSELs. I think that's great, but of course these need cooling, which I assume, right?
Sure.
And the other thing is generally VCSELs only work with SPAD, right? You need sort of SPAD in a LiDAR for VCSELs to work well. But at these wavelengths, SPADs don't really exist. I mean, they exist at the lower wavelengths, but not at these. So how would you resolve that?
Well, you know, we focus on the VCSEL chip, and of course, we need to work with other technology partners to combine it with the right type of lenses or diffusers or any kind of, you know, other technologies to make it a product inside a system. But you know, we focus on the laser side.
Mm-hmm.
So in that sense, I don't know if someone is here in the group, in the meeting today, who may be able to answer this better, this question.
We actually are having a discussion on SPAS in the infrared in a different setup with the University of San Diego. So there's something going on in that direction now at this moment. And Sabir, this is the key question. We sometimes forget about the detector side. I'm going to address that later. But Christian, your presentation also resonated with Ralph Munster from Silk. Ralph, what's on your mind?
Yes, that's very interesting. So one key question that I have to Christian is, what are they usable for coherent sensing? The power level is good, but it's maybe not good enough for a pulse time of flight. How long is the coherence length of these, or the line width?
The line widths, that's a good question. I can tell you a view of the single mode lasers have usually a single emitter has a line width of only like 5 to 10 megahertz. I don't have that data right now, but I can provide that to you.
Okay, yeah, no, that makes sense. And yeah, my father's they would be great for, I mean, the power level and so on. If they could have a line width like down to maybe 100 kilohertz, then they could be really usable for what Jan Erik has as an application, long range, because there you certainly need a line width below 100 kilohertz. So we, and I'm not sure, Jose, if I can share a slide now.
Oh, yes, of course. Please go ahead. This is your meeting.
Yeah, what kind of power levels are you looking for?
So actually, 1 watt would be plenty. In fact, 500 milliwatts or 200 milliwatts might be enough.
Okay.
And that's per pixel. So ideally, you want to do an array here. So let me see if I can share.
Ralph, please go ahead and share the screen. Yes.
Yeah. All right. So thanks for having me here. So my name is Ralph Münster, and I'm with Silk Technologies. So Silk stands for Silicon Light Chip. We the founders of Silk, some of the pioneers in silicon photonics, have been working in this area for over 25 years. What we do is we integrate all these hard-to-do components for FMCW LiDAR onto a silicon chip. And last year, we announced our ionic vision sensor, which is the world's first commercially available, fully silicon photonics integrated FMCW LiDAR transceiver. I know this is a mouthful, but here's our chip. It contains the laser, meters of waveguides, detectors that are monolithically integrated, an SOA, and in future even solid state scanning. So we are in the shortwave IR band as well. So in terms of detectors, Christian, we could talk about that. We have some of the best quantum efficiencies, anywhere from 1200 to 1600. That's where our detectors work. They're germanium based, and these are some of the results. Jan Erik mentioned that detecting 0.01 degree at 160 meters is important. What we do here is about 0.01 degree, and we can detect a scooter at 600 meter coming towards us, or a truck at 900 meter, or here the power lines at 300 meter, which are probably about a centimeter in diameter. So we are headquartered in Monrovia, that's near LA, 50 employees, about most of them are technical, 18 PhDs, and we have raised about $60 million in funding so far, and have reputable investors ranging from Osram to Sony to Faro, Epson, UMC, Yamato, and so on.
Ralph, I am in San Jose right now. Last time I was in Montana, I visited Aurora. Stefan Heinemann is here. Going to talk later. Maybe I can stop by and see your company a bit. But Ralph, thank you very much for being with us today. I want to go back to Jan Erik now. Jan Erik, we have tried to see one of the two challenges in price, which is the light source and the detector. Any final comments before we go to John Deere? How does this resonate with you?
Well, it's the total sum that makes the difference. I mean, it doesn't matter to me whether I save $1 on the detector and pays $2 more on the receiver. It's the total sum, and given that you have fulfilled the specs. So I try to be technology agnostic and look at what it does. So maybe that's a boring answer, but
I understand that this is as much as you can say publicly, but I believe that a couple of people are going to get back to you behind the lines after this call. Thank you, Jan Erik, for being with us. Please welcome. Stay, because I will come back to you. But now we go from the automotive. Veoneer is a tier 1 in automotive. We go to the agriculture market. I had the honor and pleasure to welcome to the stage one of the companies who has set the scene in bringing industry, bringing technology, bringing photonics to agriculture. I'm talking, of course, about John Deere, Zach Bonelas. Thank you very much for being with us today. The floor and the attention of everyone goes to John Deere. Boniface, sorry.
Great. Thank you, Jose. Appreciate that. Excuse me, I got a little bit of an echo here. I think I need to turn off my mic.
We hear you very clear.
Okay. You know, over my 20+ year career, I've used LiDAR in just about every agricultural scenario that you can imagine. And let me just say that the results were mixed. And over time, as compute increased and image sensors improved, more and more we transitioned our perception technology to cameras, and in particular stereo vision, but still keeping an eye on what's happening in the LiDAR industry. Primary issue for us in our environment is dust penetration. Dust is an ever-present issue in agriculture, and that is had been the primary hindrance in terms of making productive autonomous systems with LiDAR as our primary perception sensor. I think a lot of this is just physics, at 900 nanometers with eye safety, the very low power that you can output. I just don't think there's going to be dust penetration at that wavelength. So I think in order to serve the agricultural market, you're going to have to be at a longer wavelength. Our environment is very harsh. Sometimes sensors that are designed for the automotive market don't live long on our equipment. So, we need a very rugged device. Need a wide field of view, both horizontally and vertically. Our machines are very tall, and they can turn in very tight spaces as well. So if we mount a LiDAR kind of up on top of the cab, having that wide field of view horizontally and vertically would be very beneficial for us. Accuracy is also important. There are certain applications where mapping would be very useful to us and important, and having high accuracy would be helpful there. And then Doppler information, kind of at the bottom of the list, very nice to have. So there are circumstances where LiDAR odometry would be useful when GPS is compromised or just simply not available. Not needs. So rightfully so, the industry is very focused on that automotive application due to the high volumes. Certainly our volumes are not automotive, but neither are our requirements. So a lot of companies come at us with an automotive pitch, but I would invite people to stop and think about our environment and our equipment. Top speed for our equipment is 50 kilometers per hour on the road, right? And that's not really where our need is, right? We're not trying to deliver autonomy on the road for ag equipment. It's in the field where our top speed is, maybe 25 kilometers per hour. And related to our need for, not for high speeds, but for low speeds, we don't need the highest resolution as well. And then, from a crosstalk perspective, we don't have lots of equipment working together in the field in concert. And also, if crosstalk events do happen, the worst thing that could happen is that the vehicle would stop, and it would be a small productivity loss. But I think the chances of having a crosstalk incident are pretty slim. One other thing I'll say is that we've got a history of testing LiDARs and other sensors in dust chambers. And what we found is really that not all LiDARs are created equal, even at that 900 nanometer wavelength. However, we've never experienced a LiDAR that has outperformed even a passive camera in a dust chamber. But we haven't given up hope. In fact, we've invested in the construction of an indoor dust chamber that we plan to have commissioned by the end of the year. So if you're a LiDAR vendor that's out there and interested in serving our needs in agricultural space, we'd invite you to come in and test with us at our facility in Fargo, North Dakota. Anyway, that's all I've got, Jose.
Thank you very much. I really am very excited about this dust testing that you do. Is this something that when it comes to a LiDAR, I think the most difficult thing there is how it would resist the not only the light going through the dust, but also the dirt being accumulated in the optics. What is the limiting factor of the dust in a LiDAR environment?
Yeah. So definitely much more the ambient dust in the air than the dust accumulating on the window or the lens of the LiDAR, in my experience.
Okay, so I have a couple of companies here in the room that are experts in optics manufacturing for LiDAR. So I want to give them the floor, but first I see that Ralph Munster has unmuted his microphone. So maybe he wants to add a comment to this. Ralph?
No, I apologize. No, it wasn't intentional, but I certainly have a comment to that. What we missed with coherent is that coherent sensing has the capability to go through dust, and there's some nice studies that have been done by Bridge in the past for the Army, where helicopters land in the desert, and when you blow up all that sand, there is no visibility, and they've shown that you actually can look through the dust with coherent sensing. So just a comment that might be interesting to try out. We've tried it out, and we've seen through smoke and dust pretty well.
I do recommend also the use of FMCW LiDAR when it's very dusty, because it's not limited by power, and that is something that you can also reject the scattering of the light in the dust, Ralph. Yes, indeed. We have a question in the room coming from a company that is expert in integrated photonics with 3D sensing applications. That company is Anelo Photonics. Thank you very much for being with us. Tell us, what's on your mind? I think we may have lost him. I think we lost him. He raised the hand and then he was going out. It's a pity because they do 3D sensing. Okay, let's go back. I'm sure he will reconnect, but because I really have a couple of comments for you, John, for you, Zach. Zach, we really see that there is a need for optics in the LiDAR regime. So I have two companies, one in the micro optics and one in the larger optics, and I want to see there is a match with the unmet needs. So let's start with the micro optics. We go to Switzerland, the global country of micro optics, and we go to Axetris, Music. Thank you very much for being with us today. Tell us, what do you do in LiDAR with your micro optics?
Thank you, Jose. So today my voice is not best for speaking a lot because I catch a cold, but I will share the slide first. So do you see my screen?
Crystal clear. So
thank you, Jose, once again. And Axetris is the leading manufacturer of micro-optics. Shown here some product portfolios. Like we manufacture micro-optics on wafer level, like larger chips or single chips as well as arrays. And also we do diffractive optical elements. Our micro-optics are very well known for telecommunication transceivers. But today we talk about LiDAR. What is the link with the LiDAR and telecommunication transceivers? For me, it's simple. So, for example, the transmitter side and receiver side. Transmitter side called TOSA and receiver side is ROSA. This is schematic. Laser diode coupled to the PIC or PLC chips to going to somewhere to detect either to the fiber or free space. Light coming back to the receiver side. This is all I want to talk about for the LiDARs, in fact. So LiDARs. So if we talk about the optical systems, this is just one example of the optical system we can see in the optical table, but you cannot sell the product with such big optical structures. So everyone wants to go to the integrations, like simplified, like PLCs or PICs. Then coming to the coupling. So for instance, in this like ROSA and TOSA and ROSA, you have very small spaces in between the laser diode to the PLC chips or detector to the PLC chips. So micro optics is, in fact, really the necessary components. We can increase the performance within this small miniaturized space to integrate. And Axetris, we manufacture micro optics, but not only the micro optics, we can add a lot of additional features for integrations, metallizations or structurings, or sometimes like spacers. So for the soldering process as well, we can do the metallizations. So I believe maybe more key components can be detector or emitter. But connecting all these things, you need optics, especially small space micro optics. That's what I want to say today. And thank you, Jose.
Thank you very much. At the end of the day, you have done great job packaging transceivers in many applications. We are going to have a lot of discussion at the co-packaged optics event here, but I also believe, of course, at the end of the day, FMCW LiDAR is coherent transceiver. Looking at the companies in the room in FMCW LiDAR, I see that we have people from Aurora, and also, of course, we have Ralph from Silk. So there could be some comments on that. But before that, there is a company that is very active in Optica in the field of fused silica. I have Gary Bishop in the room from Dynasil. Gary, are you with us today? Gary, please unmute. Yes, okay. Yes, don't worry. You don't have to show slides. Just unmute. I would like to. So, Gary, you are very active in the field of fused silica optics from Dynasil. You also use other materials as well. How do you see the LiDAR market as an opportunity for Dynasil? What do you bring to the table?
I'm no longer with Dynasil. Haven't been there for a few years. I've been in the optics, photonics, laser industry for 20 plus years. I certainly have had more interest in the automotive side because of companies developing laser technology for delivering more power, more range, more resolution. But I was certainly very interested by the discussion on John Deere in terms of their needs and applications, because, you know, IP66, IP67 for dust prevention is not unknown in the laser industry. I developed a laser for the marking industry for going into breweries for where they're hosed down, you know, with caustic solution every day, and it had to be both watertight and dust tight, and the dust tight spec is done with talcum powder, so it's pretty damn small and gets in just about everywhere. So with small packaging for LiDAR systems, it's a matter of sealing the enclosure, and you know, just lenses on the outside surface of any imaging system are usually pretty much glued into place, so they ought to be completely dust tight at that point. But it's an interesting area to be in. I've had a lot of background and experience in the fabrication of optics, lenses, systems, sensors, and just here listening to what people's issues are and trying to see if there's a chance that I can be of help to people and bring that few decades of experience into this crowd.
Thank you, Gary. I am sorry I was not aware that you led Dynasil, but now I'm aware that you can help our members succeed. So many of you get in touch with Gary. He is great. He's been a big help for me in the last years. I'm going to continue with the meeting, but before that, there are two people in the room who are waiting to get their students, and one of them is coming from the European Space Agency. We have Paul Reyes Plezuelo with us. Paul, thank you very much for being with us this morning.
Good afternoon, Jose. Good afternoon.
Thank you very much for being with us this morning. Could you tell us what interest you bring from the LiDAR segment? What is your interest in LiDAR?
Yeah, first, Jose, I think there's some cuts in your connection. I think it's from your side. And well, I'm working in the European Space Agency, being the focal point for LiDAR technologies. So I basically oversee the atmospheric LiDARs, LiDARs for GNC, for rendezvous and docking, for moon landing. And I basically interested in seeing the developments for automotive LiDARs, because indeed, I think the automotive LiDARs are pushing for a miniaturization, and to see when this device is reaching to a point that it can be used, for example, for CubeSats and so on. So that's my idea and my purpose of being in this meeting today.
I live in Northpike, even though I'm in San Jose now, and it is great to continually having the support of European Space Agency with us. I will maybe be connecting with you later, and now continue with the meeting. We start started Pioneer, we continue with John Deere, and now we go to one of the companies who has into not only building LiDAR, but also software LiDAR needs. We go, of course, to LiDAR. Thank you very much, Pierre, for being with us this morning, this afternoon. The floor and the attention of everyone goes to LiDAR Tech.
Okay, well, thanks, Jose. So certainly my pleasure to participate here today. Let me share my screen, start my timer so I can stick to the time. Okay, so hopefully you see my screen now. Okay, so well, first of all, very quickly on LiDAR Tech. So as you were pointing out, Jose, although we're known, of course, we've been active in LiDAR for quite some time. Company, we've been in business for more than 15 years now. But certainly today we're very active on the software side on for ADAS and autonomous driving for passenger car. So certainly we're both also qualify as an end user of LiDAR. So certainly within that context, certainly as Jan-Erik was mentioning in the beginning, the specs for LiDAR for like level 3 and up are quite well known. And actually these are specs that the industry has been working with and working on for years now. And actually as Jan-Erik was mentioning, the problem is actually getting even more complex today. But really nobody's managed to check all these boxes yet. And certainly cost is a very significant one, because when the industry says low cost, they mean like $100. So basically very, very challenging goal, especially given the rest of the specs, which are indeed their table stakes. But certainly this is what the industry's need to deliver on. Certainly, as far as I took a bit different approach, what I need as a LiDAR integrator to be able to deliver these like specs, what help I need from this industry. I see it in 3 categories. Certainly, first, as was mentioned earlier, if 905 nanometer can be made powerful or high performant enough, certainly it has a significant cost benefit. So what's needed from like physics and the industry to be able to deliver this? Well, first of all, thermal drift for emitters is really what's killing 900 nanometer LiDAR. It's not so much power, it's the fact that the drift from the edge emitters is like significant enough that it limits the narrowband filters that can be used. So if there were ways to minimize that thermal drift, there would be huge benefit. And certainly VCSELs have some benefit, but they have their own quirks as well. They're heavily multimodal, and even their emission pattern is heavily influenced by temperature. So certainly lower drift emitters is number 1 on my list. Certainly more stable narrowband filters is second on my list. So if there's anybody that has work or technology that can help make very stable narrowband filters, I'm definitely all ears. And certainly third one is, okay, eye safety is the limiting factor in like 905 nanometer LiDAR. So if there's any creative solutions that can help increase apparent source size, that would be huge benefit. So again, if anybody has like specific optical construction that can help transmit like higher power while remaining like class 1 eye safe, that'd be great benefit. So now if I move, of course 1500 nanometer is seen as the way to address this, but it has its own set of challenges, and certainly cost, as has been mentioned earlier, is a huge one. So certainly lower cost emitters for 1500 would be huge asset. And certainly we've seen earlier 1500 nanometer VCSELs. That's a significant step in the, or promises to be a significant step in the right direction. Certainly curious to hear more about that. But as has been mentioned as well, the detector side is still, it's really key challenge, because even if we solve the cost issue or bridge the cost differential for emitters, detectors are still very expensive, especially as we go to like larger like focal plane arrays. So certainly any vendor that has technology to make cost-effective large focal plane arrays in longer wavelengths would be like great to hear. And certainly the other is how you deal with size, weight, and power. And certainly cooling remains an issue, of course, as we try and make these solutions smaller. We've heard about like liquid immersion cooling earlier. Maybe this is technology that could be applied to LiDAR. The issue with TECs is they're very ineffective, or inefficient, I should say. So at some point they create more trouble than they solve. But certainly cooling is a big challenge. Sensor cleaning, that's been mentioned in the for ag, but that's also true for a passenger car. And certainly I've seen developments in like ultrasonic window cleaning and so on, but still not applicable to larger size optics. So anything that can help keep the sensor clean is huge benefit. And the third one is really beam steering. So I realize I wasn't okay. Beam steering is the one of the challenges that has not been fully solved. Certainly MEMS, micro mirrors have seen significant development, but there's still OPAs have seen development as well, but there's still challenges to be met. And certainly with that, I want just to leave with what we contribute at LeddarTech is really what we call our LedDAR steer technology, which is really automotive grade digital beam steering that uses liquid crystal polarized gratings to provide really high reliability automotive qualified steering. Certainly I'm not going to go through this, but the gist of it is we provide really software controlled like dynamic beam steering. Important thing is this is compatible with both direct and coherent LiDAR. Can be made in 905 nanometer, can be made in 1550. So certainly anybody interested in learning more, just reach out to me. Okay, thanks.
Thank you very much, Pierre. Thank you for a great presentation, and thank you for positioning LeddarTech as a software company that enables innovations. And there are many in the room, people that I want you to meet. One of the companies that I would like you to meet is the company Castor Optics. Do we have anybody from Castor Optics in the room? I think we have Kathy Baudet with us.
Hi.
Kathy, good morning for me. I think good morning also for you. Kathy, I met some of your colleagues in Rochester last week, and we discussed about your double-clad fiber and how this could be an interesting approach for low-cost LiDAR solutions. Could you tell us just a bit about this?
Yes, so we developed a double-clad fiber coupler a few years ago, and it has been used a lot in biomedical imaging, but we're trying to branch out, and LiDAR is definitely an application we're looking into. So we're quite newbies in the field, actually. But what the coupler does is that it couples a single mode signal with a multi-mode signal. So the coupler for the single mode part acts as a null coupler. So the signal goes very efficiently from one port to the other. And what it can do, it can actually collect the signal back from a reflector, whatever that is, a vehicle or passenger, whatever. And then we can collect it quite efficiently with the multi-mode cladding surrounding the single mode core. And then the coupler will extract that multi-mode signal very efficiently to another port. So we can decouple the illumination from the collection of the signal. So that's what the coupler. Yes.
So what kind of wavelength can you use with the double class fiber?
So we have different variations. So 1300 is a very popular wavelength for both telecommunication and biomedical imaging. But we have version covering almost the whole range. So 1060, 780, so and probably 900, which seems to be a very popular wavelength as well, down to 530 nanometers. So if there's a double clad fiber available, actually we can do the coupler that is specific to that wavelength range.
Yeah, the same question as we asked Jan Eric, because we don't know. What is the wavelength that we should use for LiDAR?
Well, I'd give the same answer. I mean, in the end, it depends. So certainly from 1500 nanometer is very attractive from eye safety standpoint, of course, from power standpoint, but it's you pay on all other dimensions. So if the cost issues can be solved with 1550, great. If not, then 905 remains a pragmatic choice. But really, we don't have a horse in this. So we're working in both areas.
I want to ask one of our key companies in Optica, both in the field of integrated photonics and the field laser, is a company Teraxion. And I see Matthew Foshek with us this morning. Matt, good morning. Thank you very much with us today from Teraxion.
Good morning.
Matthew, when it comes to LiDAR, where does Teraxion stand? What do you supply or provide or offer to the LiDAR community?
Of course, we have developed a very low noise DFB laser to help on the FMW LiDAR. So we are offering low noise laser for that.
The narrow linewidth, low noise DFB lasers of Teraxion, who are already integrated by a couple of FMCW LiDAR in our Optica network, and you have been very successful on that. I would like to come to you later, but before I do, I've been told by a couple of people that my sound is not stable. I hope that this gets solved. We see Silicon Valley, so internet should be really fast here. But I would like to go to one person who means a lot to this industry and personally, all the way from Japan, Yoshiaki Shigata-san. Yoshiaki, thank you very much. No, it's really late for this moment to me. We have been talking about your detector cameras mostly in wavelength range. What is your interest in LiDAR, and how can I connect you with the rest of the community?
Today, I have interest in the new beam steering technology or idea, but it's too quick to explain. Could you explain a little more about the new beam steering?
Yes, tell us about the need for beam steering, Pierre.
Okay, so let me just then share the one slide if you don't mind, that I skipped over. Let me actually find the right button again. Okay, so actually, when we say digital beam steering, what we mean is the steering device uses a series of steering stages, each of which can steer in one of two angles. So basically, and each of these stages is a combination of an LC switch to control polarization and a polymer grating to steer in one of two angles. So by configuring,
you're not sharing your screen.
I'm not sharing. Okay, yeah, sorry. Let me just too many buttons. Okay, hopefully you see it now. So by controlling the polarization of each stage, we can steer it in one of a number of directions based on just the output of a control word. So what we found, and what actually most of our customers found, is that this can be very effectively combined with number of LiDAR architectures. And really, address some of the challenges. For example, you can do staring array LiDAR, but the arrays very rapidly become very expensive if you want high resolution. So you can combine a smaller array with this device, or you can combine a MEMS with a more limited field of view with this device and meet or help meet the automotive requirements. So certainly that's very, very high level description, but certainly if you're interested in learning more, just reach out to me and we can arrange a presentation. I think that's going to be helpful.
There's a question about this coming from the European Space Agency. Paul, what's on your mind?
Yes, thanks, Pierre. I think these are definitely really interesting technology. Also, I've been looking to just to know what's the optical power that the liquid crystals that you are using can handle, and what's the loss in transmission depending of the switching angle that you have.
Well, from optical power standpoint, this can handle hundreds of watts. So we've used this actually the technology's been used in like the space applications. So certainly it can handle very high power laser. From like efficiency standpoint, it will decrease with angle, but typically each steering stage can have like up to like let's say 97% efficiency and higher depending on wavelength. So for specific configuration, we can quickly model what the overall transmission curve would be versus angle.
Thanks. I think there's a question. Yeah, sorry. I also agree with the next question about the kilohertz, or the hertz that you have. What's the switching speed?
Well, switching speed is typically it's microseconds per step. So typically in the order of up to up to let's say depending on which if you're driving or relaxing the liquid crystal from tens of microseconds up to like hundreds of microseconds.
The next question in the room comes from music from Acceleris.
Thank you, Pierre. So this solution look like very wavelength sensitive, like polarization gratings and quarter wave plate and half wave plate. So in previous question about wavelengths, you said you're looking for both wavelengths like 1550 and 905, but according to this solution, I think your primary wavelength is 905 only, I guess.
No,
or you have solutions for both wavelengths.
We have. You're very right that for a given device, it's optimized for specific wavelength. But we can produce devices tuned to like customers' preference in wavelength. So one of the benefits of the technology is we can very rapidly produce variants. So within weeks, we can provide samples tuned to customer specific switching angles as well as design wavelength.
Okay, in that case, you develop this in-house by your team, or this is outsourced? Because if you talk about you can quickly change the wavelengths and providing like test samples for the different angles, I have that question.
Yeah, no, actually, this is a technology that we produce, we develop, and we industrialize. So certainly, we have the supply chain both for prototyping as well for mass production ready.
Okay, thank you.
Next question in the room comes from Silk Technologies. Ralph Munster, what's on your mind?
Yeah, Pierre, I love your LiDAR steer. It's a great approach. Generally, what the drawbacks with these solutions is the switching speed, and you mentioned that it's about 10 to 100 microseconds, which is good. I mean, it's good for the slow axis, not good for the fast axis. But what are the losses going both ways?
Well, typically it's going to depend on number of stages, and you're quite right. This is a solution that's optimized to be used with other like steering means, which can be like, for example, an OPA for the fast axis or whatever, or MEMS, or 2D array, or 1D array. So certainly we're not designing this to be able to deliver like hundreds of thousands of steps, more like tens or hundreds of steps. So in this case, overall efficiency can be it really depends on number of layers, but anywhere from let's say 60 to 80%.
Great. We'd love to try it out if you have it ready for 1550, for example.
Definitely happy to talk. You know where to find me.
Fantastic, Ralph. I contacted you yesterday for this event. It was worth it being here. Thank you very much. And before I go to the speaker, I want to give the floor to a very good friend coming all the way from Canada, Alain, consultant from Optica Inc. Thank you for being there. What's on your mind?
It's a question for Pierre.
Alain?
Is this for a bistatic or monostatic system? Because you send a polarized light, but the light that's coming back is going to be blocked if it's not exactly polarized the same way. So if there's any depolarization, you lose the system.
Well, if there's any depolarization, you'll lose some of the efficiency. So certainly we've demonstrated this both with monostatic and bistatic configurations.
Okay.
It is time to continue. We are taking the second hour of the meeting, second hour bringing a person who means a lot to Optica. Xavi Ramvala, thank you very much for being with us today, and plus your experience, your vision, and your perfume for LiDAR. Xavier, you are muted. Yes. I think
Sorry
you are
about that.
muted.
Yes. It's great to be here. Thank you for organizing this Optica. I think it's a great forum.
Can you press Control L so we can see full screen?
Oh. Can you see it now?
Still, we don't see it full screen. You go View and then full screen.
Hang on.
In the menu, do you have two screens in front of you?
Yeah.
Yes. Go to slideshow mode.
Can you see it now?
Yes, now it's perfect.
Okay,
yours.
great.
Yes,
so,
perfectly.
Very happy to be here. And the thing I wanted to focus on was, LiDAR miniaturization, right? And the reason is, I consult with a lot of companies that make LiDAR, but also use LiDAR, right? And I also write for Forbes about these topics, and I interview a lot of people in the space. And I think over the past 2 years, the whole idea of miniaturization has become a big deal, right? And so I just want to explore why and sort of what are the barriers and things like that. So the obvious reasons, of course, for why LiDAR should get miniaturized, right, is of course it enables easier vehicle integration in terms of location, styling. It makes things easier, right? And so that is definitely a very important reason. But really, the not so obvious reasons is, if you really think about it, as LiDAR, if you can make smaller LiDARs, right, with of course the required level of performance, it of course implies a higher level of integration and very importantly a lower number of piece parts in the bill of materials, right? And of course the lower number of parts in the bill of materials does lead, if designed correctly, to higher yields, lower BOM costs, lower process alignment costs, capital and labor, right? And so this whole idea of cost actually gets driven as you're able to miniaturize the LiDAR, right? And so that's kind of the not so obvious reason, right? And what are the enablers to getting into smaller LiDARs, right? And so, of course, the first key enabler is to maximize semiconductor content, right? In everything, in the laser, in the detector, the driver, the compute, and how you address the field of view, right? You have to be able to minimize mechanics, right? And by that, I mean large scanners, rotating systems, things like that. I think having optical fibers and fiber lasers is a problem because it's going to lead to a constraint in how small you can get. Using thermoelectric cooling leads to hermetic packaging, and that also increases size. And then, of course, using PCBs, right? I think you're going to need to move to ASICs, which most people are doing, right? And so in terms of scanning, right, and this is point 3, using either flash, electronic, or optical scanning, and really, so that's purely solid state and no moving parts. And I include MEMS as a moving part, actually, in that whole scheme. So I think having really no mechanical movement is kind of the one of the key enablers, right? And so what are the challenges, right? So scanning without mechanics is difficult today, in terms of addressing practical field of view requirements, right? Lasers do generate a lot of heat, okay, and so this sets a lower bound actually in the end of how small you can make your LiDAR, because you need surface area to kind of manage the heat. Silicon photonics integration is great, but that whole area is still maturing. I think it'll get there, but I don't think it's there yet. And then you're forced to use certain, bulk optics and other elements like circulators and isolators, and these can also limit miniaturization, right? So those are the challenges. And so, yeah, there was a lot of discussion about eye safety, and wavelengths always matter. I think in my experience, the wavelength is one of the very emotional subjects when LiDAR is discussed, right? You've got people who are, passionate about one wavelength over the other. I know in my past life, I was very passionate about 15xx nanometer LiDAR, right? For obvious reasons, right? And so this is actually, it sort of compares what's happening with LiDAR, but I just wanted to focus on issues of miniaturization, right? And which is really, think about laser and detector temperature sensitivity, it is lower in these wavelengths, right, versus the 15xx nanometer regions. And the need for hermetic packaging of optics, it's a maybe here, but here you more or less have to do it, right, for reliability reasons and because you're using cooling, okay? So that's kind of one point about miniaturization. And then, of course, the availability of higher power VCSELs, they certainly exist now in a very mature way in the 8xx, 9xx nanometer regions, right? I had a no in there before, but I think things are changing here. The higher wavelengths, people like IQ and Trump are reporting higher wavelength VCSEL developments, although I think it's going to be limited for LiDAR because SPADs are still not available in this regime, right? And not generally available, okay? And then, of course, if you look at higher coherency lasers, of course, at 1550 you have it, and you don't have it here, right? So, so I think these are the factors that are going to determine how you miniaturize LiDAR, right? And so then I talk a little bit about some of the techniques and the players, right? So of course, flash LiDAR or approaches using solid state scanning. So VCSELs certainly at the lower wavelengths offer a pathway to electronically scan LiDAR, right? So Ouster, IBO, OPSIS, they all sort of work in that region. Of course, there's flash LiDAR, Continental kind of was one of the pioneers in that, and then Ouster Sense was the other one, right? So that's purely flash LiDAR, so complete semiconductor solutions, no moving parts, right? Now, OPAs and tunable lasers and silicon photonics-based CMOS, okay, is another pathway, and there are players there, right? Sorry, I forgot to mention Silk in here, but certainly Intel, AIBA, Aurora, Insight, Silk are all in that game. The LCM technology for optical scanning that Lumotive is working on, and as I learned today, LiDAR Tech also has a solution to this, is another tool. And then, of course, there are other techniques, MEMS switch fabrics, for solid state scanning. And, people like Voyant and Draper are kind of promoting this, right? So that's kind of one enabler, right? And so then, of course, the second thing is the high levels of photonic integration, silicon photonic chip scale LiDAR, which is going to be indium phosphide based. And, the whole integration into sort of a semiconductor solution, typically coherent FMCW. And then, of course, VCSEL and SPAD arrays, right? And the latter, this is important, the SPAD arrays at the low wavelengths are made in CMOS with optics and electronics integrated in a single chip, which I think is a very powerful sort of enabler for miniaturization, right? Now, eliminating active cooling, right? I think it's very difficult today for indium phosphide-based systems. I think the lower wavelength systems seem to get away without doing active cooling. And then this, the bulk optics, for things like focusing, that's of course a challenge to miniaturization, but there are emerging metamaterials-based optic solutions coming in, for example, from a company called MetaLens, right? Which is actually heavily miniaturizing the kind of the lens dimensions that you need to focus light in things like LiDAR, right? Or camera. Okay, and so this is simply a snapshot of where things stand today. I tried to obviously categorize based on wavelengths and physics. Some of the companies and really what the physical sizes of their LiDARs are, right? And so really what caught my eye, of course, was Baraha, affecting almost a factor of 10 reduction from what they reported. I guess maybe Jan Erik is helping them, but in collaboration with Veoneer, going to a pretty small size, actually, even though they actually use a mirror to scan the slow axis. Insight, I think, is also pretty, I think, good. And so anyway, this gives you, and I did want to, of course, talk about sort of performance and really the metrics I use is, points per second and range, right? Because this in the end, as people like Jan Erik talked about the fact that you need a minimum level of performance and that includes range, resolution, speed, and all of that stuff, right? But this gives you the range. And so this, it's, I guess in my mind, some of the approaches using time of flight 1550 are big, I think, because they use fiber lasers, right? And so this is going to be a difficult nut to crack unless you move into semiconductor diode lasers, right? IBO is, of course, they're using scanning with no moving parts. And so anyway, this gives you sort of a range of where people are on the miniaturization front. If Baraha pulls this off, I think that's great. But I think that's going to be sort of a lower limit to size, given that you need to meet certain kinds of performance parameters. Right? So that's really what all I had. Thank you for the opportunity.
Thank you very much for this. It is priceless to have you in the room. We have a couple of people who want to comment on this. The first one is Christian Neumeyer from Vertilas. Christian, I see your hand is up. What's on your mind?
Well, of course. So thanks very much, Sabir, for your good and compact overview. I just wanted to comment on two topics I saw in your presentation. One is, of course, you have this table with availability of technologies, and it says there's no 1550 nanometer VCSEL available. I have to say that we've been shipping 1550 nanometer VCSELs for probably 16, 17 years now. Of course, for other applications like for communications or for gas sensing. And we have produced 2D VCSEL arrays for 1550 already a couple of years ago. But at that time or in the past, there was not so much interest in long wavelengths 2D VCSEL arrays. And so you're mentioning IQE and TRUMPF here. But I'm missing verticals on your chart.
Yeah, no, I apologize.
I mean, we got it. I mean, so we got the long wavelength VCSELs, and we're doing 1550 nanometer for a couple of applications. And now, actually, in this first step for 2D arrays, we have focused on 1.3 micron, like in the range like 1380, 1350 nanometer for special regions, or for for the demand that we get from customers. But as I said, we've done 2D VCSEL arrays with 1,000 emitters on one chip already a couple of years ago. And as we do it for 1.3 micron, we can just do it for 1550 nanometer based on any requirements. So if there's anyone in the room, like Pierre from LiDAR or anyone who's interested in 5050 or any other wavelengths, long wavelengths VCSELs, please contact me, and I can tell you what our technology can do. There's one comment, and then you mentioned this active cooling requirement for indium phosphide based solutions or lasers. I'm not sure. It sounds very general, so I think you need to look into the requirements. I mean, our lasers, our VCSELs are very efficient. I mean, the wall plug efficiency is not as good as for gallium arsenide VCSELs. But if you want to have like a 1.3 micron or a 1.55 micron laser, there is only indium phosphide. So if there's a technical reason to do that, you need to work on 1550, or so you need to work with indium phosphide. And if that requires active cooling, I think it's really depending on your heat sink and how you drive the lasers. Because if you have short pulses, you probably don't need that. But this is more a question to the system experts rather than only to the laser guy here. But those were two things which jumped into my eye, and I wanted to comment on.
Well, I think the cooling. So I first of all apologize for not including. I wasn't aware, and so I am now. But then that's good to know. But I think the cooling piece. I know of no 1550 nanometer system, both on the laser and the detector, that can survive an automotive temperature range without some active cooling, right? It just won't work, right? I mean, so I think that's for 1550 systems, given the physics of the material, I don't think there's a choice. I think you have to actively cool unless you're locating it inside the cabin, but then that leads to other problems. Right.
What temperature range are you looking at when you say for?
Well, it's the usual, the automotive range, which is I think -20 to 95 degrees, right?
Yeah, there are various. I mean, some are thinking like 85 or 95, but
it doesn't matter.
Up to 120 if it's engine management. So it depends. But our lasers can go up to like 80, 90 degrees. It really depends how you drive the lasers. And as I said, this is a question for system companies, but I'm not sure if this is really a law.
Christian, let's follow up on that. I need to move on now. In Europe, there is a big project called the Tinker project that they are aiming for 3D printed additive manufacturing used for autonomous sensors. And they are very interested in LiDAR. They contacted me because they wanted to show you, Sabir, what they do. So Thierry Mounier is here representing CEA Leti and the Tinker project. There is a bit of echo, Thierry. I don't know how we're going to solve it. I leave you the
let
floor.
me check if I can solve that. Is it better now? Do you hear me?
Yes, it's better now. You can go ahead.
It's better now. Okay, so thank you for giving me the opportunity for giving a few words on the photonic technology perspective, and specifically the packaging of the LiDARs for miniaturization. So let me share my screen.
Bottom of the Zoom window, there is a green arrow up, share a screen, and then very important, select the screen that you want to share with us.
Yeah.
Yes, it's coming.
So, okay. Oh, sorry. I was too fast. Okay, do you see my screen?
Yes.
Okay. So I'm Thierry Mouillet from Leti, CA Leti. We are a technological RTO that is working on the photonic developments, and we are involved in the Tinker project to work on the miniaturization of the LiDAR for the autonomous vehicle driving. So just to get out of this mechanical steering devices for driving, which are huge, slow and expensive, then the technology moves toward typically steering devices named OPA, optical phase array, that are based on working on the CMOS compatible silicon technologies. And we are working on this technology by generating the steering through heating. So here you can see an emission reception of 256 channels optical phase array, and with the different devices that are embedded. So typically silicon oxide, the grading couplers and waveguides, all the interconnects, and as you see on the pictures below, the nitride heater that will generate the wavelength shifting. And using this technology, we can generate the beam steering at 20 kilohertz to make the LiDAR. Sorry. However, big difficulty is that the autonomous vehicle driving will require a lot of antennas and a lot of channels to fulfill the requirements in terms of beam accuracy. And as mentioned on this picture, using conventional technologies, that you will have to embed typically more than 500 wire bonds. That's becoming quite critical for a manufacturing perspective. So in the Tinker project, we are working on adapting 3D packaging technologies that were already developed for the conventional electronics to photonic ICs, and through the use of the attachment of the OPA on a photonic on a silicon interposer. As you can see on the picture here, the emitting OPA on a let's say a test silicon interposer, and we can imagine the interposer not only for testing, but it can also we can add on it the CMOS common devices, and eventually when they are ready, the lasers to be coupled with this OPA. And for that, we work on different technologies. That the first one is, of course, to develop the interposer and all the let's say the features on it. Second way is to integrate the TSV concept to be able to move all the connections from the edge and the front side of the OPA toward the back side and all the surface, which can lead to drastically reduce the footprint of this device. And when you've done this transfer of all the interconnection on the backside, then you can integrate high density collective flip chip technology. Typically, in this case, we're working on 20 micron diameter copper pillars, and this leads to a very dense connections toward the interposer. And combining all these 3D, we believe that we can highly reduce the footprint of the OPA for beam steering. Thank you.
Thank you very much. I don't know, Sabiri, you have any question, comments? Yeah, tell us.
Yeah, quick question. I mean, so the thermal wavelength shifters, right? I mean, they're typically quite slow, right? So I mean, how are you able to address large fields of view at a high frequency?
Yes, the picture is quite slow, but this is just because it was a probing on a probe. Typically, the performance we have in steering is we can do a 2P at 20 kilohertz. So
I'm sorry, could you tell me again? You said you can. What field of view are you addressing? I mean, how many points are you doing per second? How many points can you scan per second?
In fact, we do the 256 channels, moving from 0 to 2P scanning in 50 microseconds.
Okay, thanks.
Thank you very much. And Sabir, many people are going to be asking you questions offline. Thank you for this great overview. I would like to remind everyone, the meeting is going to be in YouTube minutes after we finish, going to be in YouTube for everybody to watch, or you register, you have access to a version of the slides. Thank you much for that. We go to the next, and for that, we go to the US Army Ground Vehicle Line. Welcome Robert Sadowski in the room. Robert, thank you very much for being with us. The floor and the attention of everyone goes to you. Robert, I think you are muted.
No, I'm fine. I was just trying to get my slides to come up. Or my slides come
perfect.
Up? So yeah, so Bob Sadowski, Ground Vehicle Systems Center. I'm going to talk about a little bit different customer perspective than what we've been talking for automotive and mostly on road. Actually, we have a lot more in common with John Deere, and we operate in a domain where, quite honestly, it's not always friends that we're talking to, working with. So there's some challenges that we have to face, and thank you. Let's hit the next slide. There we go. That are kind of unique to our domain, and I'll hit some of the needs that we have in the 5 minutes that I have. But basically, what I always like to try and tell folks is that I've got to operate within a space that's very, very challenging and very difficult across a variety of mission sets. So we do big robots, small robots, subterranean robots. All those need LiDAR in some form or fashion. However, having a system that actually emits on the battlefield that the enemy can see is always a challenge. And so we are looking at passive techniques as well. But when you think about what we need to do with logistics and what we need to do with subterranean work, LiDARs become very important, because the subterranean work, I need to do mapping, and all the stuff that works at the 905 nanometer range is fine for that in terms of dense point clouds to do that piece. So let me just jump ahead a little bit and say, what are my desired ground LiDAR character challenges? Okay, I was really loving the conversation that you all were having about wavelength. Okay, so the Army likes to fight at night, and having a sensor that lights you up like a Christmas tree and flashes at 10 hertz is basically saying, here I am, come find me. And so our customer, the warfighter out there, really wants to get something that's beyond the sort of silicon band. They don't know what that means. I tell them, hey, you got to get past 1100 nanometers, predominantly because what happens is even the low light silicon sensors with an IR filter, you can pick up the LiDAR quite easily. So it doesn't mean I have to punt totally LiDAR. However, all the work that's being done at 1.3, 1.55, so on and so forth is very interesting to us. You kind of heard John Deere allude to this already. Our worst enemy, and you can kind of see the video running there, is we make our own dust clouds. Because a lot of times when you're doing cross-country off-road maneuver, or you're actually on secondary and tertiary roads, predominantly tertiary roads, they're dirt. We make our own dust. And we live in our own dust, and it's not really good. You have to work through it. So clearly the longer wavelengths help there as well. The other problem we had, and you kind of heard John Deere talk about this, is we have to deal with extreme environments, and some of those environments, the high shock value, we're looking for solid state sort of devices or anything, even MEMS I think would be fine in terms of being able to steer. Now, one of the challenges we do have is that I can't just stick a single LiDAR on the platform, and it's not going to sit on top of the vehicle. We're probably going to put it within an enclosure because we're moving through brush, we're moving through terrain, and we have to ballistically protect it. So the coverage doesn't, I have to get 360 coverage around the platform, but I'm not necessarily within a single sensor. Of course, cost is always an issue, but for some of the military specific requirements, we can go to a higher price point. I saw some interesting work that your folks were talking. We're thinking the same way. If with existing systems, I can dynamically alter angles, power, relationships. So for example, if I'm trying to go through dense brush, I don't need to see and travel at 130 kilometers per hour. I might be doing 45 kilometers per hour. So if I can dynamically alter the angles or potentially the power levels, I can focus on that. It was good to see some folks talking about polarization, because I need to determine the difference between a steel rod or maybe a chain link fence that I may not be able to traverse with smaller robots versus it's just grass, brush, things along those lines of typically negative obstacles. And then the last piece I'll talk about is I like where you all are trying to go with smaller, and this will work with 900 nanometers. We're pairing vehicles, unmanned ground systems with small UASs, getting back to the fact that we fight at night despite all the videos you see out of Ukraine. And the sort of small UAS pairing where I can actually actively map, because the enemy tends to modify the terrain and basically let our platforms and our systems operate in sort of this modified terrain. And that's kind of all I wanted to, from a sort of customer perspective. We're kind of unique, but again, it's all about trying to offset danger from the soldiers, sailors, airmen, Marines who operate these platforms. And LiDAR is one of those things that I can actually make a mathematically provable case to my safety community. I may not have NHTSA, but I actually have a testing community, and I have to prove that I won't hit something at 1 part per million. And some of the vision-based techniques, I'm not sure if I can do that. So I will be partnered with vision-based technique, learning-enabled components, and LiDAR for a little bit of time. And that was really pretty much all I wanted to kind of cover there, and open the floor up to questions. I really like the lively conversation we're having here. And oh, by the way, I will neither confirm nor deny that I used to do lasers way back in the day out at Stanford. Over.
Thank you very much for being with us. There are many things that we can discuss at the moment. It is right now the open room for cooperation. And I always like that in the last 3 online industry meetings that we had the of the US Army and the different sector to tell us what they need and how room for cooperation there is open. So my first question, that direction, as you know, we do here a global industry network. So there are companies here that are coming from Germany, from France, from Singapore. Is there any limitation when it comes to the supply chain, the geographical origin of the company?
Not necessarily, because a lot of foreign companies will have a U.S. presence that you can buy from a U.S. manufacturer. The challenge we'll have are things that might be sourced in certain countries that we're having challenges with right now. But other than that, we do buy components from all over the world. Supply chain is always an issue, but it is a global supply chain for these components. Over.
Okay, so are there any questions, comments, or ideas for cooperation in the room for Rob?
I have a quick comment here.
Ralph, tell us.
Yeah, Robert, I love your challenges, the slides, they are great. And you mentioned polarization is important to you. And I wanted to share with you real quickly. The Silk coherent LiDAR is also giving you the polarization intensity back. So what we do is we send out linearly polarized light, and then on the return back, we can give you both polarization intensities back. What that does is it helps you to, when you mention steel, fences, and rods, it actually is really good in detecting metal, or in this case here, I'm standing next to a mannequin, detecting human skin versus non-human skin. Here's plastic or other kind of surfaces and materials. So I think that's quite unique. And in terms of the big picture, most of the sensors today, they just look at the photon intensity as they come back. With our approach, we actually dissect the photon itself and look at its wavelength, polarization change, phase change. So give a lot more information back, like instantaneous velocity, which is the Doppler shift, or kind of information about the material. So maybe we should connect. I think that could be a good thing for your ground vehicles.
No, appreciate it. I actually wrote down your company's name after you gave your little talk. We are definitely interested also in the ground plane buried objects like mines, and IEDs actually show up very well in cross polarization. It would be great to get that out of a LiDAR versus just being able to have to do that specifically with some large EO systems over. Thanks.
Thank you. And one more point is actually we can scale down the power level. So while versus time of flight requires like kilowatts of peak power, I mean, it's really bright and, and visible. We can actually detect with down to 10 milliwatts of laser power, 100 milliwatts. We can, I mean, even sub 10 milliwatts, we can get 20, 30 meters. So it is actually pretty, I mean, scalable. So you get to kilometers with maybe like 500 milliwatts, and you get to tens of meters with 5 milliwatts. So very little power, hard to detect. So thank you.
Bob, when it comes to the aspect ratio of the LiDAR system, is there any limitations or specifications, both in aspect ratio as the weight, size, anything that affects the payload? Bob, you're muted. We lost you.
Yes, so you came a little distorted, so you probably had the classic SWaP-C question, it sounded like.
Yes.
Size, weight, power, field of view. I mean, we use all sorts of different LiDARs. We got Luminars, Ousters, Velodynes, obviously. So it depends on the platform. It really is very dependent. So I'm doing everything from 30-ton trucks and automated HIMARS all the way down to basically robots that basically that are about this large. So SWaP-C is always a concern, but it really depends on the application that I'm trying to look for. So we are looking for a host of LiDARs across that. I'm not as, we use the 900 nanometer LiDAR, but I can tell you my customer, particularly when we're talking about vehicle robotic combat vehicles, really does not like something that can be seen so easily on the battle space, as you can imagine. So but however, for some of the applications that we have in the rear area, 900 nanometers works perfectly fine. And particularly for some of our cost conscious applications for material handling equipment, for example, hey, that's 900 nanometers is fine. Because if basically the enemy can see you moving forklifts and equipment around, you get some other problems. Okay, so I'm trying to be a little glib about that, but that's kind of the perspective that we kind of take over.
That's exactly what I was expecting you to say, that a light that can be visible easily was not the ideal one. Jan-Erik from Veoneer has the hand raised.
Well, thanks, Robert. Yeah, thanks, Robert. I enjoyed your talk. You mentioned you create your own dust, and I can see that. And dust quite often has smaller particles, but then you get fog, and you have different, depending on where they are, coastal fog, inland fog, or whatever we refer to it, the particle size. But then you get into water spray behind the vehicles, and I guess you're also walking in convoy on wet roads and so forth. So when you talk about higher wavelengths, I understand what you mean by going away from wavelengths that can easily be detected by silicon. But how much does going to 1550 or something around there help you in penetrating your obscurance? Is the wavelength really that important? Because that's basically our conclusion, is that, well, we can throw more power at the problem with higher wavelengths, but it doesn't really solve the problem by penetrating the obscurance, because even if you go up to long wave infrared, you have problems in where you have substantially higher wavelengths. Throwing more power at the problem is good, but there are other means to get rid of the backscatter that is needed. But what is your experience? Because you have a different point of view.
Yeah, you're bringing up a whole series of questions. So in terms of fog, yes, vehicle spray would be when we're on road, but a lot of the vehicle spray doesn't occur when you're off road as much. So it's kind of more of a mitigating effect. Yeah, snowstorms and blizzards are always an issue. We test up in Michigan, and it's already snowed here. It's unfortunately sad to say. It didn't stick, thank God. That's while I was out in California, so my family thanks me for that. In terms of some of the pieces that we think in order to get through, so we're not going at the very high speed, so we'll probably have to use visually based techniques in the IR beyond NIR. So some of the thermal cameras you can see through fog pretty good. You can actually see through the obscurance that the enemy puts on the battlefield, unless they're using something like graphite in the mix, which gives you a sort of, it'll block all thermal. So that's called hot smoke versus cold smoke. So we're looking at a variety of those different techniques. Again, what I try to tell folks, there's no one size solution that fits all the problem sets that we have to have. We have to do a sort of multimodal sensor fusion in order to get around some of those challenges. And our platforms are sort of human supervised, as I always like to tell folks. So we're not fully autonomous. No, we're not making automated killer robots. So, you know, having multiple of sensor systems to kind of solve some of the mobility challenges, I think what we're gonna have to do near term. That's also one of the reasons why we're looking at SUAS pairing as well. So a downward look to help pair and help the robotic system navigate over it. Hopefully I answered your question, sir.
Yes, thank you.
Daniel Zhu from Intel has a question for you, Bob. Daniel? We cannot hear Daniel. Let me see. Otherwise, I will read the question. Bob, what is the reliability requirement for military application? Did I hear it right? DPP.
Okay, so you need, again, it sounded like you were talking degraded visual environments and liability requirements. For some reason, I was getting a lot of delay. And so your voice stretched out, Jose. Was that the question? What are the military liability
question is in the chat. You can read it in the chat. Please read it out loud.
Okay. Now you're gonna make me go down to the chat, which is fine, which is okay. The welcome chat. Okay,
what is the reliability requirement for military applications?
Okay, so what is no. So the 1 part per million is not the reliability requirement. The reliability requirement is usually in the high 90s, 90%. They'll have a mean time between failures based on mission success. The 1 part per million I was actually referring to is my safety case to get to a medium safety risk. So I have to validate, usually mathematically, to get to a medium safety risk to 1 part per million of a catastrophic accident. So for example, if I have a visual perception system that says my robot can't run into anything, then I have to show to 1 part per million, which is almost impossible to do test to under a variety of conditions, that I will not actually have my autonomous platform run into somebody. We work it through the Army Test and Evaluation Command, and there's a military standard 882 ECHO that we have to follow, though we've been more carefully looking at for autonomous systems to follow what aviation has done under DO 178. Those are numbers that, you know, normally I would think you all probably are not as familiar with, but it is actually, we get independently tested, so we don't self-assess. These folks are independent testers, and it's a joy. They're a joy to work with. Over.
Thank you very much for that. And thank you very much, all of you, for a great, great meeting. I would like to remind you that this was, for us, an intentional way of connecting our members with potential needs from end users, and we did our very best to make that happen. I would like to apologize once again for the connection, the internet connection here in my hotel. The next one I'll organize from home, and it will be far more reliable. But just to give you a quick grabs of what happened in the last 2 hours, we have Veoneer talking to us about the specifications for automotive. Then John Deere talked to us about their way that they do for LiDAR in agriculture, and especially on the dust testing, which was spectacular. We had a great presentation from the US Army, in which they talked to us about their challenges for LiDAR and LiDAR tech. And that was for me the highlight of the event, when we talk about the different beam steering solutions. This was Jose Pozo representing Optica together with Tom Hausken and Elise Frisgage. We did our best to connect the industry and will continue doing so. Once again, thank you very much for being part of Optica.